believe is, first of all, I'm Associate Dean for College of Science, so Department of Mathematics, just for your information, is a part of a College of Science. Okay. Number two, I just told our speaker today that although I'm a physicist, my father is a mathematician. Okay, so there's a natural link there. And by the way, I stayed in Switzerland for a couple of years for my PhD in Geneva. So I just flew back from Zurich a few days ago. So also a link to our speaker today. All right. Just to start, let me say a few words and give a very general introduction to today's lecture and our speaker today. So this lecture is one of the highlights of the, as you are all aware, Hong Kong IES, International Conference on Mathematical Analysis, and its application. So we are deeply honored to have with us Professor Alessio Figalli, currently Senior Fellow of Hong Kong IES and Director of the Institute for Mathematical Research at ETH Zurich, and a recipient of the 2018 Fields Medal, one of the most prestigious awards you can have in mathematics. Right? So Professor Figalli, born in Rome in 1984, is an Italian mathematician. After completing his bachelor and master degrees in mathematics at University of Pisa, he obtained a joint PhD in mathematics between Pisa and Lyon. He held faculty positions in France and United States before joining the current institution in 2016 as a chaired professor. So since 2019, Professor Figalli has served as the director of the Institute for Mathematical Research. Professor Figalli's research spans the calculus of variations, partial differential equations, and optimal transport theory, where he has made profound contributions that bridge pure and applied mathematics. His pioneering work has advanced the understanding of geometric and functional inequalities, as well as the mathematical structures underlying numerous phenomena in physics, probability, and more general, the natural sciences. For these outstanding achievements, he was awarded the Fields Medal, and of course, among many other distinctions and recognitions, for his contributions to the theory of optimal transport and its applications in partial differential equations, metric geometry, and probability. So in today's lecture, Professor Figalli will introduce us the elegant mathematics of optimal transport, a concept that originated in the 18th century and has since evolved into a central tool connecting mathematics, data science, and beyond. So before we start, may I invite the organizing committee members to come on the stage and just to grasp this moment and take a picture with the speaker. Shall we? Please.
May I please invite Professor Charlotte, Professor Amari, Professor Sir John Ball, and of course, Professor Figalli for a group photo. And Professor Lee, please.
So we already have the first round of applause, but yeah, we cannot wait anymore. So without further ado, please join me in giving a very warm welcome to Professor Alessio Figalli as he presents his lecture, Optimal Transport from A to B and Beyond. Let's welcome. Thank you.
Well, thank you very much. So for the slides, so I just put them. Oh, wait, the slide show them from beginning. Okay, good, great. So thank you very much for the great introduction. It's a big honor for me to give this lecture, and thanks also, to John, Habib, Philippe for allowing me to be here and to give this lecture as well. And also thanks for the organization. Thank you, Sophia, and all the staff for what you have been doing. So the lecture today is a lecture where I would like to give an overview of optimal transport. It's a topic that has been part of my research for many years. And it's intended as a not a lecture just for mathematicians, but more broadly for scientists. So I hope everyone can enjoy it. I will not use formulas or anything, despite just the scary first slide, right? That's supposed a bit to impress, but doesn't mean anything. So this is optimal transport. So what is optimal transport? Optimal transport started with Gaspard Monge, French mathematician, who started to study this problem a bit before the French Revolution. And so you see, in Monge period, something which was very important was for military application to find the best way to move material from one place to another. So you have material which is extracted from the ground, you want to build fortification, and you want to do that efficiently. So so again, you have this movement of particles, right? And you see that you think the following, right? So if I have to move material from one place to another, I will have a cost associated to it. This cost can be either money, but it could just be workforce. I mean, I want to be efficient even for the people who just have to transport the material. And so the goal is that I want to transport this material from one place to another in the cheapest possible way. So whenever you talk about optimal transport, first of all, you have to decide what does it mean to be optimal. And in particular, this means that you have to decide what is the cost needed to transport material from one place to another. So in his first study, Gaspard Monge thought that a very natural choice of cost would be the travel distance. So if I have to, 1 kilogram of material, and I have to transport it between two cities, which are 100 kilometers apart, I will pay 100. If they are 1,000 kilometers apart, I will pay 1,000. So the cost is really proportional just to the distance between the two destinations. So this was Monge's model. He wrote his a famous paper, as I say, just before the French Revolution. And then in this paper, there is a lot already of beautiful geometric insights. So he kind of studied the problem both in the two-dimensional situation, so in the plane, or in three dimension, like the space where we live. And he managed to prove a bunch of properties of this optimal transport map. So he found several geometric insights on how optimal transport should behave. Then, of course, mathematics evolves more or faster or slower, depending also on what's going on in the whole community. So the 19th century was not the right moment yet for this problem. And despite some contribution, let's say the big next revolution took 150 years. So we had to wait until 1940s before, let's say, some really new deep mathematics was done for optimal transport, and this is due to Kantorovich. So Kantorovich, Russian mathematician, he studied the Monge problem in a different way. So the problem of Monge formulation was the following. In Monge mathematical formulation, he was not allowed to say that if I have 1 kilogram of mass, I can just break it in two parts, alpha kilo, and then perhaps alpha kilo goes to one destination, alpha kilo goes to the other destination. Sometimes you had let's say, a minimal unit of mass, but then this unit of mass could not be split. In the mathematical model of Monge, you just had 1 point. Once the mass was at location X, it had to go to a location Y predescribed for that mass. So I could not decide that mass could be split. Kantorovich rewrote the formulation in a slightly different way. what we call now Kantorovich formulation. And these allowed, for instance, to mathematically interpret the optimal transport problem in a way that you could study situations like the following. So imagine here the following situation, that you have some bakeries and you have some coffee shops. Bakeries produce, I don't know, croissants. And in honor of the French here. And so they have to supply different coffee shops. And you see perhaps, so you know each bakery how much produces. You know each coffee shop how many croissants are needed. So let's say depending on the size of the circle, it means more or less croissant needed, and depending on the size of the square is how much the production it is. And what you want is to allow for a single bakery to supply croissants to multiple coffee shops, but it could also be that perhaps you want some coffee shop to get croissant from different bakeries at the same time. So here we are not looking for a single optimization. So it's not a single bakery or a single coffee shop that's tied to maximize profit. The idea is that we cooperate. It's a cooperative game. And the goal is just to find the best solution for the community, which is we minimize the total transportation cost. So we just want to be efficient. So all play together, bakeries and coffee shops. So you see, the optimal transport problem here becomes just a simple optimization problem where you just want to draw arrows, and the arrows tells you the arrows tells you whether some croissants are sold from one bakery to a coffee shop, and also depending on the intensity of the arrow, how many go from one location to another. Of course, if you have 4 bakeries and 10 coffee shops, it's not a very complicated problem. But I will mention later situations where in reality the size is not 4 versus 10, but probably it's like 1 million versus 1 million, and then this optimization problem becomes, especially at the computational level, extremely challenging. So for this, what was very important of this formulation of Kantorovich is that it made the optimal transport problem a convex optimization problem. He developed a full mathematical theory from that. And in fact, for his work, Kantorovich received the Nobel Prize in Economics in 1975. So this is, here we're in the 1940s, and then now optimal transport has been developed much more. It has become a very robust mathematical theory, and it has application in a bunch of areas. A natural one is urban planning. People from Zurich may recognize this is Zurich. So an example of good urban planning. For example, in urban planning, let's say you know where people live, you know where people have to work, and then you want to build an infrastructure system so that perhaps you minimize the total commuting time of the population, things like that. There are models in meteorology which use optimal transport. We saw this also in some talks during the conference. I will come back to that. There are models in biology, image processing, machine learning. Some of these examples will appear in my lecture. But so now it's kind of a theory that has application in many areas. So let me give an example of optimal transport. So this is what people found could have been an explanation of my contribution to optimal transport theory. And this is a comic by Leo Ortolani, who is an Italian comic writer. And you see that his interpretation of optimal transport theory is the following, right? I found the cheapest way to go from one place to another. And you see me caught by the police without a ticket. So that's one possible interpretation of how you solve the optimal transport problem. I strongly discourage you from doing that, especially if you live in Switzerland, even more. That's one interpretation. I hope to give you a different interpretation also of what I did besides this one. So to explain you, so I would like to give at least 2 different situations where optimal transport appears, and I would like to show them also because it's not clear why optimal transport should be there. I think what's nice about optimal transport is not only that it is a theory that you apply naturally in some optimization problems, so you just minimize transportation costs in concrete applications, but actually it arises in situations where a priori there is no optimal transport to start with. So let me start with a different story. So I will forget optimal transport for a moment. I will tell you a different story first. So let me go back now by a bit more than almost 3,000 years. So we are back now in the 18th century BC. So this is the so-called Dido's legend. So Dido's, she had to flee her city because her brother killed her husband. This is very common in the mythology of the period. And then she had to escape. And then she sailed with some of her servants. She was sailing through the Mediterranean. And then she landed on the kingdom of King Jarbas. And then she asked the local king for some land. So she came with some gold. And she said, OK, I would like to buy some piece of land to build a new city. Now, the local king said, OK, for the amount of gold you're offering me, I'm going to give you as much land as you can cover with the skin of a bull, which usually is not that much. Even if you take the skin, I don't know, it would be smaller than this room, right? And then Dido, she was a very smart woman. She accepted the deal. She said, sure, I will do that. Here's the money. But then what she did is that she took the skin of the bull and she cut it into very thin strips. So out of the skin, now she had very thin strips that then she took and she sewed them together to get a very, very long cord, long several kilometers now. And then she had this cord and she said to the king, you know, the deal is the following, right? As much cord as I can enclose with the skin, I'm going to get, that's what I get as a land. So now let's see what I can do. And what she did was that she took the cord and she drew this semicircle. And then inside, she built her city. And this was the foundation of Carthage, the city of Carthage. So Dido is considered, this Dido legend is considered the beginning of a mathematical problem, a very classical mathematical problem, which we call as mathematicians the isoperimetric problem. You see, Dido was given a cord which was long, I don't know, let's say 10 kilometers. And then she had to decide with that cord which shape to give to it in such a way that the amount of land enclosed by the cord was as much as possible. So it's a mathematical problem. Of course, in this picture, you see, OK, the Carthage is not exactly a semicircle, but it's not that far from it. In this picture, you see that in her case, Dido could take advantage of the coast. So because she was on the coast, she drew a semicircle. But of course, if you're not on the coast, you don't do the same. So if you are in the coast, you will do that. But if you're in the hinterland, you will draw a circle. In fact, it's no coincidence that most cities, actually, especially in the old days, they all has either a semicircle plan or they were circular. So I'm giving you already the solution here. This is the best choice. But it's not totally obvious. I mean, if I asked you, can you prove that you cannot do better than that? There are by now several mathematical proofs of this result, but I would say there is no 5 minutes proof that you can find. I mean, or if you can find a proof that you can give in 5 minutes, I would be very happy to hear about it. Because I think every proof that I know either requires a bit of more advanced mathematics or the more elementary ones that require a sequence of, an argument that will take quite some time to close up and give you the full result. But the problem, mathematically, we can formulate in the following way. So you have a curve of a certain length, as in Dido, and you want to enclose the maximum amount of area. And let me reformulate this in a different way. So you see here, what in Dido's situation, the length was given, 10 kilometers, and the goal was to maximize the area. But there is a dual way of formulating the same problem, which is fix the amount of area you want to enclose, and let's minimize the length you need to enclose it. So it's the same thing, just from two different perspectives. So you can minimize length among curves enclosing a fixed area. So these two problems are the same. You solve one, you solve the other. So if you are in the plane, well, the solution is given, we know it. There are many proofs. If you are not in the plane, not in 2 dimensions, but I ask you the similar question in higher dimension, this problem becomes much more tricky. So in 3 dimensions, for instance, our space, you will fix the amount of volume that you enclose. You have a 3-dimensional object. You fix how much volume you have inside, and then you want to minimize the surface of your object. That would be the isoperimetric problem in 3 dimensions. And then you could ask the same thing. What's the best shape in 3 dimensions? And if you're in 3D, the answer is given to us by soap bubbles. The answer is a sphere. So why soap bubbles? The soap bubbles are the optimizer of the isoperimetric problem for physical reasons. Is because when you play with soap bubbles, what you do, you take the soap bubble, is attached to a wire, and you blow air inside the bubble. Then the bubble detaches from the wire, and then once it detaches, the bubble closes up. Once it is closed up, the amount of air contained inside the bubble is fixed. So you block the volume. The air cannot go in and out. So the volume is fixed, and then what the bubble can still do is to change the shape in such a way as to minimize its energy. And the energy tension of a bubble is the same as, for physical reasons, isotropy, is the same as the surface area. So the bubble at the beginning is a bit, bubbly. But then it starts to move and suddenly it becomes very quickly a round sphere. Why? Because this is the configuration of minimal energy. In physics, every configuration wants to go to the minimal energy state. And that's why we see always round bubbles. Of course, this is not a proof. I mean, it's not a mathematical proof, but it goes in this direction, right? Okay, so bubbles are the object that optimize this volume to area ratio. So after soap bubbles, you can go further, and you can look at crystals, for instance. So it was in 1878 that Gibbs realized that the same way droplets or bubbles arrange themselves so to minimize the surface energy, this happens also for crystals. So for instance, a crystal is not 2-dimensional. This is a 2D picture of a 3-dimensional object. But the reason why crystals have a certain shape is because of the same reason that the soap bubbles are round, is because they minimize some surface energy. The point is that the surface energy of a crystal is different from the surface energy of a bubble. And so is the surface energy that tells the crystal which kind of structure it should take. So it's a crystalline structure that depends on the properties of the molecules that compose the crystals. So you have to go to the atomic structure. But the principle is the same. You are still minimizing surface area, some kind of surface area with fixed volume. So this was Gibbs' realization. And then it was the question that you ask is, are these configurations stable? So what do I mean by this? I mean the following. If I take an energy configuration like this, the crystal. So I told you, or let's think even the soap bubble. I told you the soap bubbles are round. Truth is, if you check the soap bubble, a real one will never be perfectly round. For very simple reason. There is gravity acting on it. So the soap bubble actually will always be a bit more squeezed in this variable compared to the horizontal one, because gravity will push it a bit. So the potential energy. Or perhaps there is wind. And if wind acts, it will move the bubble a bit and it will deform it a bit. So these are just idealistic configurations, but in real life, the temperature is not 0 Kelvin, it will be more, so it will deform. There are many forces that act on a physical system. And so the fact that we still observe something which is almost round is an indication that these configurations are stable. You cannot break them by adding just a bit of energy. They can deform, but they will not be broken. And in some sense, mathematically, we would like to see this. And perhaps we would like even to understand to which level these configurations are stable. So the question that we ask ourselves is the following. So suppose that I give some energy to the crystal, perhaps by raising temperature. That's just an example. Or as I say, that you have extra energy from outside, you have gravity, whatever. How much will the shape change based on the amount of energy given? So I want to find a relation between the energy given to the crystal and the change in shape. So let me call epsilon the amount of energy that I add to the system. So let's say this is my ideal crystal, perfect pentagon. Then the temperature of the system goes a bit higher, not too much, but a bit. And this will slowly deform it in a new configuration that I expect to be close by, but it will not be exactly the same. So here, okay, is just a caricature picture. I'm not saying that you will ever find a crystal like that, but let's say that K epsilon represents a possible crystal you can find after you give epsilon amount of energy to the system. And now the question is, if only information I give you is this is a pentagon, and I tell you how much is epsilon, so I give you this number, can you tell me how much that shape changed from the original one? So can you quantify the change in shapes only in terms of epsilon? So this is the mathematical question. So now, where is optimal transport? So optimal transport is about transporting objects. But if you think this process of heating, I have my ideal crystal. This is a zero energy configuration. And then I start to raise the energy in the system continuously. So particles will move along this kind of path where the energy goes up. And then they will reach a new configuration, which has an epsilon amount of energy. So I can think of optimal transport as a way to follow the movement of particles through this process. And so you see, I have kappa, I have kappa epsilon, and then I have a map T that tells me how the molecules move, each single molecule move from there to there. So I kind of can encode my change of shape into a transport map. So it's a strange thing, because optimal transport has nothing to do with the question I asked you. The question is just about crystals, so some crystalline structure, some surface energy, and some energy. But optimal transport is like, it's a mathematical tool now, becomes just, okay, I have these two objects. Let me look at the transport between them, how the particle moved from configuration to configuration. I just use it as a mathematical tool. And then through this mathematical tool, I try to get informations of how this shape changed in the process. And then I will do some mathematical manipulations. I will get estimates. And then in the end, I will reformulate that in terms just of kappa and kappa epsilon. And that's exactly what we did now 15 years ago. In 2010, we proved that if you give me epsilon of energy, the shape can only change at most by square root of the energy. And this was already known in 2 dimensions since many, many years. But this is a general result, which is true in every dimension, and actually is true for every crystal. So we have bound, which is independent both of the dimension and on the crystalline shape. So this was the first result we proved through optimal transport. And of course, and this theorem is independent of kappa, which means that the same theorem holds for soap bubbles. So soap bubble is just a particular example of crystal where everything is isotropic and you are perfectly round. Of course, if you are really a crystal, which means that you have like this polyhedral shape, I mean, I challenge you to find a crystal which has this shape. You will never find something like that in nature. So in fact, this theorem that we wrote was very general, so you couldn't do anything better than that. But then, of course, for crystals, you would like to prove a stronger theorem. And that's what we did 10 years later with Zhang, when we proved that actually the crystal cannot change its structure. So we proved that even if you give me an amount of epsilon of energy, and you start, let's say, from a pentagon, then the minimal configuration will still be a pentagon, and each side of the pentagon, this side will still be parallel to this one, this side will still be parallel to this one, and so on. So the pentagon can be slightly deformed, but in a very rigid motion pattern. And this is true in every dimension. So it's not only true in the plane, but even if you are in high-dimensional crystal, 3-dimensional, for instance, in nature, then the only thing you can do is just to move slightly the sides parallel to each other, but there is nothing else that can happen. So the crystals are extremely rigid objects. So here, optimal transport is one example where optimal transport intervened to understand a problem about showing robustness of minimal energy configurations, where optimal transport, you don't see it in the problem, you don't see it in the final statement, but it's really a key mathematical tool in the middle to prove this result. So this was example 1. Now let me give you example 2. The example 2 is probably more visible. So we had already a talk by Beatrice about this topic. Is about the semi-geostrophic equation. So let me give you a kind of a simplified picture of the problem. Let's say that you look at clouds, and you look at a cloud at certain instance of time, t0, and you look at the cloud again, I don't know, 1 second later. So from the outside, all you can see is just a cloud that has moved. But then you remember that clouds are made of particles, small particles of water, well, not 20, but probably some billions. But okay, here I only drew 20 of them. So there are these dots, which are the individual particles that compose the cloud. And then I could ask the following question. If I tell you that these 20 points went to that 20 points, can you tell me exactly who went where? So can you tell me which point on the left corresponds to which point on the right? Just by looking at the picture. No extra information. So, okay, of course, if you're only 20, perhaps you can start to guess. I don't know, you will tell me, okay, probably this one corresponds to this one. I don't know, the one on the top is the one there on the top, and so on. So you expect, of course, some kind of some continuity. But can you find a way mathematically to find the right matching? And it was in the early 90s that Mike Cullen, British meteorologist, realized that there is an optimal transport problem behind it. So the coloring, the pairing between left to right, you can do it by solving an optimal transport problem. You want to transport the points to the left to the points to the right in such a way that the total transportation cost is the least possible. For which cost now? Remember, the choice of the cost is important. So for Monge, the cost was the distance. So cost to transport a point from x to y is the distance between x and y. Here we are in a physical system. So the cost is not the distance, but is the distance square, because it's like the kinetic energy. I mean, the kinetic energy of a system is v square. And then from that, you naturally get to distance square. So it's a kind of, it comes from kinetic energy. So you can just look at this problem. So you see, but just looking at the dots and solving an optimal transport problem, I could find the exact pairing of points. So this means that optimal transport could be used, because of this kind of intuition, I could use optimal transport to solve the equations that govern this movement of atmospheric fronts. So I have some partial differential equations. These are called the semi-geostrophic equations, which are kind of complicated. And you would like to use optimal transport as a way to solve them. The problem is the following. You see, you can do that. So there has been a lot of work to do that. But even if you understand, let's say, the movement of particles, in reality, what you want in the end, for physical reasons, you want always to reconstruct the velocity of the cloud and the pressure of the cloud. So these are the physical quantities that appear. So people were able for many years to say, okay, I can understand the movement of clouds through optimal transport, fine. But they had problems to reconstruct out of this movement what was the velocity of the cloud and the pressure of the system. And this is what was missing. And it was something that, so the connection has been known for more than 20 years, but there were some results about the regularity theory for optimal transport that was missing in order to kind of close this connection, OT to so from optimal transport to semi-geostrophic back and forth. So, so I remember when the first time I heard about this problem, it was in 2005. And this was my advisor, Luigi Ambrosio, who mentioned to me this connection. And I found it very interesting, very fascinating, the fact that optimal transport could be used to study this problem. And I remember starting to look around, study some papers, thinking about the problem. And when you try to, and in this case, it was very clear what was the statement you wanted to prove. So it was very clear the theorem you wanted, but you didn't know how to get there. So here is like a metaphor of that, right? You know where you want to go is the top of the mountain. That's the theorem. And I want to get there in some way. And perhaps to go there, I will need to prove a bunch of results, some lemmas, whatever. But you know, when someone tells you, prove this, there are tons of different ways you can try. And then when you try, most likely you will get stuck. And when you get stuck, there are two questions. Did I get stuck because I just need to think further how to advance? So am I on the right path, but just I don't know exactly how to go to the next step? Or am I completely on the wrong path? I just took a way which made me advance a bit, but I just took the wrong path. And then there is no way from that direction I can go to the top. So which is, this is probably one of the most frustrating aspects of research, that most of the time we are stuck, and most of the time we don't even know if we are stuck, for which reason we are stuck. Most of this, most time when we try to solve a problem, the problems are difficult, so we get stuck and we remain stuck. Sometimes things go well, and then you find the right path. So it took us a lot of trial and error, and essentially the key result was found almost 7 to 8 years later. So we published the work with Guido De Filippis in 2013. So it took a bit more than 7 years to understand the right path. So with what we did with Guido was that we developed the theory on the required theory for optimal transport that was needed to make the connection, and then we wrote a paper with Ambrosio and Colombo where we showed how then this could be used to solve the semi-geostrophic equations. So this is a case where we finally found the right path, but I have many situations where I'm still back on the bottom of the mountain and I don't know how to go up. And that's fine. That's life. It's fun. So this was just another example where optimal transport plays a role in a different topic. So you see, I'm trying to show you that optimal transport is, okay, of course, it's a problem by itself. It's a very interesting mathematical problem, but actually it has connection to many other areas, and it can be a powerful tool. So these examples are mostly old examples. Well, old, 2013, depends how your lifetime. But for some of you, it's probably, looks recent. For others, you will look like prehistory. I don't know. But let me try to show you something a bit more modern perspective. So what people liked about optimal transport, among many things, among the theory, is that it can be used to define a sort of distance between objects. So optimal transport, I told you, it's about transporting objects. So let's say that I have, here this is, I think, the only formula I wrote, really real formula. So I have some distribution of mass that I call mu, so just distribution of sand. And I have another distribution of mass that I call nu. So mu and nu just represent my two distributions. And my goal is to transport mu to nu in the most efficient way. So that's the optimal transport problem. But then you could say, in reality, I don't care what is the best way. I only care about one number. The number tells me what is the minimal cost. So I can say the minimal cost to transport this distribution to distribution is, 3.5. And distribution to distribution is 2.7. And these two are very close, is 0.001. So it's just a number. It's the minimal cost. So you can formulate this in the probabilistic notation. You have two random variables, x and y. X are distributed according to mu, y distributed according to nu, and then you just minimize expectation. And c is the cost. So the c that I put inside, which is the subscript c here, is the minimal cost. So wc of mu nu is what? Is a number which tells you the minimal cost needed to transport mu to nu, knowing that the cost to send x to y is given by little c. So little c tells you how much it costs to move just one particle, and wc is the cost to transport now a distribution of mass. So this is just a number that measures how far are two probability distributions. So how far are two distributions of objects. So optimal transport defines a sort of distance between objects, between distributions, and it becomes a very flexible tool because there are many things you want to compare. let me make some examples. So probably the first example where optimal transport was used, or one of the first ones, for this kind of idea of transporting objects was done in 2010, Rabin, Delon, and Goussot. Here, what they did was that instead, there are two things you can do. So if you have images, you can, of course, transport images. Images are made of pixels, so you just move pixels. Here, instead, what they did was that so they took an image, like this Renoir. They took a second image, this Gauguin. They looked at the histogram of colors coming from this image and from this image. So you just extract from each image how much yellow there is, how much blue there is, how much green, and so on. You extract this information. And then they had two distributions of colors. And then they transport one distribution of colors from one image to the other. So you see here, they kind of took the colors here. They found a pairing between colors from here to here, and then they push it back. And then they colored this image. So they did color transfer. And then at the end, they do a bit of filtering to clean it up. So no one will do this now in 2025. I'm not saying that this is a up-to-date tool to do color transfer. But it's just a way to show you that, optimal transport came as a very concrete tool, transport objects, transport material, transport whatever, material for fortification, but you can transfer whatever you want. You can transfer color, you can transfer pixel, you can transfer anything you want. So this is just the first example. This was done 15 years ago. After that, there has been more work, and probably another example, which is more recent, in a different spirit, is the following. So this is about GANs, which were introduced in 2014. So in GANs is an example where now we start to get into kind of machine learning. You have the following situation. So you have, let's say here, so you have to think of a generator and a discriminator. So here you have a generator that wants to generate fake images. So let's say here are the real images. So here, let's say I give you a collection of a billion images of dogs. So you look at a billion images of dogs, and then out of them you want to say, okay, I look at this image, I want to be able now to generate fake images of dogs. This is what the generator wants to do. So the generator look a bit over real samples, and by looking at real samples, it gets an idea of how a dog looks like, and then it will start to generate image out of its knowledge. And then you want the image, the fake samples, to become more and more realistic. So what do? You take the samples, and then you send them to another computer, whatever, neural network, that will discriminate. So the discriminator, what it does is the following. It gets fake samples, and it gets real samples, sometimes real, sometimes fake. And then it looks at them, and it will give a feedback. It will say, I look at the image, oh, this image is a fake one. Or it looks at the image and say, oh, this image is a real one. And then, depending on whether the discriminator has been correct or not correct, there is a feedback given. So if the discriminator, for instance, look at a fake image and says, hey, this image is fake, this feedback is sent back to the generator that realized that the image that it just produced was a fake one, so he has to improve that. So then the generator improves there because he knows that this image was easily detected. Instead, if the image was fake and the discriminator was wrong, so he said he thought the image was a real one, then the feedback is given to the discriminator. Say, hey, be careful, he tricked you. And then the discriminator then learns how to discriminate better. And by this game that they play one against the other, they both improve. Here the goal is not to, here is a generative problems, so we don't care to have a good discriminator, all we care is to have a good generator. So the goal here is to have a tool that generates very well fake images. So this was introduced as a model in 2014 by Goodfellow and co-authors, and it became immediately very popular, but it also had the drawback that it was very slow in training, so it took a lot of time. So what was proposed a few years later was to use optimal transport. So let me just try to explain to you what this picture means. So the idea is the following. So you have your here. So in the Wasserstein GANs, which is like the optimal transport version of GANs, you forget about the discriminator. There's only one generator. So the generator, it's this one, is these arrows. So what the generator does is that it has a huge parameter space, and then it starts to generate, a huge amount of images. So these are the images. So theta is the parameters that you can optimize. So a generator has the possibility to optimize over some parameter space, and it will generate a bunch of images, depending on a parameter theta. So these are this is the set of fake images. And now nu represents the set of real images. So what do? You try to, so you have, I told you, optimal transport allows you to compare distributions. So here you have like 1 million real images, 1 million fake images, and optimal transport allows you to compare all together at once. So you compare them and you look how close the fake images are from the distribution of real images. And then you say, are they close enough? Great. Are they not close enough? No. Let's improve on so let's change the theta. So theta is the parameter I can move. This is I minimize over theta. And I try to optimize theta so that this collection of images which are fake are as faithful as possible, so they are close to the real ones. So optimal transport is a way to remove the discriminator part in the training and just use this kind of optimal transport metric in order to compare images. So the only message, the theta and this kind of parameters are a bit for people who are familiar a bit with machine learning, but the message is just the following. So you have a system that generates image, and all you can do is that it has infinitely many ways of doing that. This is the theta parameter. And then you just, for each theta, you can look at this bunch of images it can generate, you compare with the real ones, and you look how close they are. And then you just try to change theta in such a way that this space of fake images gets closer and closer in the optimal transport sense to the space of real images. It's a tool. You see, now optimal transport has just become a tool to measure distances. And it's actually an interesting tool. I will come back to this problem later. So, but this is, let's say, this prototype problem, minimize optimal transport distance between distributions and then minimize over parameter space, is like a prototype problem of most machine learning issues. So you just find a minimum. You see, finding minima, in general, it looks like mathematically very easy, but usually these are non-convex problems. So finding the minimum is extremely challenging. How do you find a minimum of something which is very high-dimensional and non-convex? It's not so easy, right? You could move theta and then go completely off, and you're like completely off from the space of global minimizers. So this is a challenging problem. Another development that appeared 6 years ago was in single-cell genomics. So this is an interesting situation because what happens is the following. So if you look at cells, living cells change over time. Think of a cancer. Healthy cells become, they develop cancer perhaps, so a bunch of them will become, sick cells, unhealthy. So you have this process of cell evolution over time. So perhaps all the cells at the beginning live in a certain space, and then they start to mutate over time. And this picture is what people use in genomics since many, many years. It's called the Waddington landscape, which it's a way to visualize cell evolution over time. And then the problem when you look at cells is the following, that if I give a bunch of cells and I tell you what's happening in these cells, what you can do is to say you have these living cells, you can take a small sample and analyze them. But the one that you analyze, you kill them. So they're not part of the body anymore, right? It's like if you take some cells from my skin, you cannot put them back. So you take some cells, you measure them, and you see something, you say, okay, that's, I think, what's happening in their body. But every time you measure, you kill the cells you're measuring. So usually in these kind of situations, you cannot do too many measurements because every time you kill the cells that you're analyzing. And then you try to make some statistical assessment of what's happening. And in particular, you don't measure all the time. So perhaps you measure the cell one day, you measure the cell 24 hours later. But what happened in that 24 hours? So the idea of Schimminger and his co-authors was to use optimal transport as a way to, let's say, close the gaps. So in some sense, by just looking at snapshots, okay, I measure my cells now in 6 hours, in 12 hours, 18 hours, and so on. I look at all this cell evolution over time, and then out of that, I use optimal transport as a way to guess what happened in the middle. So out of just looking at the cells at time T1, T2, T3, with optimal transport, they fill the gap and they start to draw a line in the middle. And this kind of guides the cell evolution. So they have a bunch of work that's been going on now for many years. Schimminger was the founder of this, has been part of his research over the last 6 years, was exactly how to use optimal transport to kind of do better prediction and create models for this single cell genomics. Now, if you want to use optimal transport in any concrete application, the challenge is that you have to be able to do computations. So, if you're a pure mathematician, you don't care how much time it takes to do a computation. Just say the solution exists or whatever. There is a theorem that guarantees that everything works. But if you really want to go at some moment to real concrete applications, I give you a problem like before with images. I have millions of images. Each image consists of millions of pixels. How do I compare them? How do I even compute these quantities? I have computationally, these are very challenging problems. So if you go back to Kantorovich, in Kantorovich picture, I had 4 bakeries and 10 coffee shops. Okay, that's an easy one. But now suppose that I have n bakeries and n coffee shops, and then is of the order of several millions. Then a standard optimization problem to try to solve that will be of the order of n cube, which, if you are millions and you start to do cube, it's a lot of zeros. So people asked, is there any way we can improve that? And right now, I would say that one thing that really made a big difference in the computation aspect of optimal transport was an idea introduced by Marco Couturi in 2013, and then has been very well described in this book by Marco Couturi and Gabriel Perret, is to use entropic regularization. So what they did is the following. They said, okay, I have the optimal transport is like a perfect matching. I'm matching points to points in a perfect way. But in reality, if I just care about the distance, I don't care about perfect matching. I'm happy with some small of blurry matching where I make small mistakes. So they have this regularization parameter, which is part of this entropic regularization. When instead of looking for a line, it's like, no, I don't look exactly for a line. I look for something like this. It's not exactly a line. It's some blurry image of a line. And that's not perhaps the optimal transport, but it's very close to an optimal transport. And that's enough. And suddenly, just by using this small trick, what happens is that this problem becomes from n cube became n square, theoretically, at the level of computation. But truth is, that's what Marco Couturi always told me, is like, truth is, it is never n square. It's always much, much faster. So theoretically, perhaps it looks already still too big, but in any concrete computation, it goes so fast that they're super happy with it. So Marco has been using these kind of tools. First, he was working at Google. Now he's working at Apple. He uses this all the time, and he says any advancement that has been done doesn't beat yet on the practical application of this entropic regularization tool. So the fact that now we have a way to compute efficiently optimal transport is something that makes it much more appealing for application, because now you know how to compute it and you can do it fast. So there have been some recent questions that kind of connect optimal transport even more theoretically to recent research. So let me give you an example. So this picture, perhaps some of you have seen it already. Some, I don't know. This is how you would depict a neural network. And this is a very special neural network because it has only one hidden layer. So you have some inputs here. You have a single output there. And you have your hidden, so-called the hidden layer. And the goal of in a neural network is what? You have to choose the intensity of the connection between these dots, the neurons of the network. And so you have a bunch of parameters, theta 1, theta 2, theta 3, so one for each connection. So there are many of them. I mean, here it could be a lot of points in the middle. And the question is, how do you do this training? So what you want to do is like the problem I told you before. You want to find the parameters theta that tells you how strong my neurons are connected in such a way that in the end, the input to output map does whatever it has to do in the best possible way. So for instance, you could use this to do, for instance, digit recognition, right? So you give a digit, you give an image here, the neural network works on it and then tells you, okay, this image was a 9, this image was a 5. So this is what I don't know, if you want to read the postcodes or whatever. So what do you have to do? You have to train your network to recognize images. And so the training of this single layer network, it turned out that mathematically is nothing different than what people have been doing in optical transport for more than 20 years, which is what we call the optical transport gradient flows. This was a study of Felix Otto. So when you write, instead of optimizing the theta 1 to theta n, you can build a measure out of them, just the empirical measure associated to the weights. So sorry if these last couple of slides are a bit more technical. There are some formulas again. But then you can write this optimization here as a PDE, and it has a structure which is a bit of which is like time derivative of this measure is the divergence of gradient of a variation of the loss function. And this is what people in optical transport have been doing for more than 20 years. This is called an optical transport gradient flow. So here there is really a theoretical connection between training a single layer neural network and solving a parabolic equation, which is of the structure that people in optical transport know very well. Of course, there is a drawback in this story. This only works for single layers. So for multi-layers neural network, when you have an extra layers, there is no such interpretation, and it's not because we are not able, there cannot be such interpretation. But so this is another connection of optical transport to machine learning. And then finally, I would like just to go back to the same problem as before. Training a neural network is usually an optimization problem. You have a parameter space, theta, so theta could be very high dimensional, and you minimize some distance between distributions. So this is what people do all the time. And usually, as I told you, these problems are non-convex, which make that extremely challenging. Now, how do you find minima of these functionals? Usually, when you want to find minima of these functionals, what you do is the following. You do a gradient flow. You take this energy, and you try to follow the gradient of the energy and move along the gradient of the energy. But now, if you have a non-convex functional, a gradient flow of something non-convex, we may not converge to a minimum. We can get stuck in many places. And then this is a bad thing. But the funny thing is that in most simulation, when people just run this on a computer, they discover that when you look, especially with this optical transport distance, optical transport seems to convexify some problems in the sense that you run it and it goes very quickly to a minimum without any issue. So despite the problem with non-convex, at a numerical level, it just converges as if it was a convex problem. And so understanding why, in many situations, it could be very important. So at the moment, we're still missing a real theoretical explanation of why things go better than they should, things are better than they should be. So there are some cases where actually we can even do that. We have some model cases with Cantan-Merigot and Filippo Sant'Ambrogio, where we have a theoretical explanation of why this happens. But in general, for an arbitrary, let's say, machine learning problem, we don't. But at least for some particular cases, we start to understand why this happens. And this has connection with many problems of not only optical transport machine learning that I think every developments could be very interesting, both for application, but also for our theoretical understanding of of this kind of problem and of machine learning. So I hope from this presentation I could give you a kind of idea both of what optical transport is, what you can do with it with math, and why in the last few years it has been also kind of become appealing outside of the math community. And these are just some examples. I didn't cover everything, of course. I just gave you my very personal perspective on it. And yeah, I hope you appreciate it. So I thank you for your attention.
Thanks a lot. Yeah, it's honestly speaking, this is the first math talk I attended since the last few years, I think. Yeah, wonderful talk. Thank you. Yeah. Now the floor is open for a question, comments, please.
Thank you for a fascinating lecture. So my question concerns the optimal transport, the combination of the optimal transport and some aggregation diffusion PD models, which may have the gradient flow structure. So could you illustrate further that how the optimal transport viewpoint can provide some new insights into the the blow-up mechanism description and some singularity formation in this kind of PD models? Thank you.
Okay, so let me try to put this in perspective with respect to what I said, right? So, so what the question is referring to is essentially this. Yeah, this. Sorry. Yeah, here. So many PDEs can be written in this form. There is a whole class of PDEs. And you can put the heat equation there, but you can put also models in aggregation, dynamics, whatever. So there are many PDEs that are of that form. Now, because they are, if you can find a PDE and you know the PDE as of that form is a gradient flow with respect to optimal transport, it means few things. First of all, it means that there is an energy governing it, which is decreasing in time. So that's already a good Lyapunov quantity for your system. You will have usually a dissipation term, which is how the energy dissipates. That's also that information which is useful to understand convergence to equilibrium over time. But then your question is, how do you work with what about blow-up? So the good thing of working with optimal transport is that optimal transport allows you to work in the space of measures. So measures can be singular, they can have Dirac deltas. So in that sense, from the theoretical viewpoint, so you can just go on. You can write the PDE is in the sense of measures. You don't have to say, oh, now my measure is singular, I have to stop. You can just go on, it still makes sense for many energies. So you have a theory which allows you to prove existence. And sometimes you can even use it, for instance, if the energy is if the functional is not too non-convex, let's say you have some kind of one-side convexity bounds, you can prove stability. So it will tell you that, okay, you have a system, perhaps the system blows up, fine, but still I have a system which is well-posed, I have a well-defined evolution, and perhaps is even stable with respect to the vastness and to this optimal transport distance. So that's what optimal transport can do for you. Now, if you want to understand really the blow-up mechanism, I want to understand what's happening at that point, it's difficult that optimal transport can help you there because in a sense you are trying to understand a very local problem. So optimal transport is taking the whole picture and just analyzing the whole picture at whole, and it gives you a global information. Now the only way there is to go down to PDE techniques like blow-up techniques or analyzing. But there, okay, of course, if you do blow-up, you can hope that the blow-up of your system, like rescaling, will still be a gradient flow. So you can try to blow it up and still make at least locally the gradient flow structure survive at a local scale, which depends on the scaling you're doing. But it's not clear that it can tell you much more than that, right? At some moment there is, there is what I would call soft analysis, like hard analysis, not because one is easy and the other is difficult. It's more like, one is soft, like more, it looks at the global picture, like optimal transport can do, and use global properties, like contraction properties of solutions is usually never local property, it's a global property. And then you have very precise quantity, like how does it blow up? What's the shape of blow up? And there you need a local PD analysis. So it's rare. I mean, maybe there are some special cases where it can help, but most of the cases then you have to go to PD tools. So optimal transport will not give you, it cannot be the magic box that solves all for you.
Okay, thank you. Yeah.
Okay, thank you very much for the very exciting talk. So my question is about what about the Schrodinger equations, quantum mechanics? Well, because optimal transport try to basically look at the density and try to link the particle dynamics with the density. Quantum mechanics, we also have the kind of like wave equations, but there's something new about the phase. So I'm not sure you know any existing will try to any potential application of OT to the problem related to the quantum mechanics or the density function. This year is also the 100th anniversary year for the invention of quantum mechanics. Yeah, I hope to help your comments.
Yeah.
Great.
So to be faithful to the anniversary, I should give you an answer which is useful this year, right? Now, so I remember when people were doing, this gradient flow from this study of using optimal transport and gradient flows came from the work of John Dakin and Rotto and then Otto, so we are roughly 98 to 2000, right, 25 years ago. From there has been a lot of work and development. Now, if you take the Schrodinger equation, what you will do is the following, right? So you will write, so Schrodinger equation is about a complex function, psi. Then you will look at the density, psi bar, so the psi square, the normal psi square. This will be your, on which you have a continuous equation. And then you have an equation for the phase. The problem with Schrodinger is that the phase, even for linear Schrodinger, the phase is not always well defined, right? Because when the density is 0, the phase is not defined uniquely. And this creates all this. So even that when you write the Schrodinger in this optimal transport way, first of all, it's a system because you have the equation for density, the equation for the phase. And second of all, it's a singular system because where the density gets to 0, you are not sure what to do because just psi was rho e to the I, square root of rho e to the I phi. But then where rho is 0, the density is not, the phase is not defined. So in that case, I don't know. One could hope that perhaps there are some situations, special situations where things are better. But I remember that, linear Schrodinger, it's easy, right? You have an explicit solution. If I just give you the linear Schrodinger equation without potential, you just complex Gaussian. And then, which is super easy to do in Fourier. And now with optimal transport, you're stuck just because of you don't know how to define because the rho is not well defined. So my impression sometimes is that there are, so optimal transport is a tool which can be very powerful and very useful in some situation, but there are situations where, okay, maybe we didn't understand yet how to use it, or perhaps there's a situation where it doesn't work. And quantum could be one example. So it's like I gave you this proof of the, no, I didn't give any proof, but I made you this connection with the isoperimetric problem, right? So I told you, you can use optimal transport to study the stability of crystals and stability of soap bubbles. So why were we able to do that? Because back in the 80s, people understood how optimal transport can be used to study isoperimetric inequalities. The inequality I told you, volume versus surface area. And everyone got very excited by that. And then there was this question, okay, you do it in the Euclidean space, Rn, or R2, R3. What if the space is curved? What if you're on a sphere? Can you do the same argument? So I give you a crystal, I give you a soap bubble, but it's not in flat space. It's in a curved space. Sphere, hyperbolic space, anything, even the simplest models. And everyone tried and no one succeeded. So this proof doesn't extend efficiently to any curved space. So over time, people found other ways. There have been even results using different kind of transport techniques, which have been actually very powerful. But the original proof that people use on the Euclidean space just doesn't work. So all I say is that optimal transport can work very well, and sometimes it just doesn't work. And the truth is, we don't even know why. In some cases, just you work so well, and you move away so little, and then suddenly collapse. So it has a rigidity in it in the moment you try to use it for a very specific problem, I think. Here, at least in the recent application, there has been the kind of big excitement, I would say, in the CS community about this optimal transport. There are many people now in CS departments who study it and use it. But here, because they're using it as a soft tool, they measure distance, they measure they measure like how far is a distribution from another. They don't care if there is a bit of entropic regularization. Then it becomes very robust as a quantity. But if you're just trying to do something very precise, I would say either it works or it doesn't. Perhaps you have to invent something different. But yeah, for the quantum, I don't know. Still, we don't know how to do linear Schrödinger, so I'm a bit pessimistic on that. So I'm sorry for Schrödinger for the quantum world. But if I can say one thing, actually, is that the entropic regularization that Marco Couture introduced, the one I mentioned before, right, for computational purposes, he didn't realize when he proposed it, and many people didn't realize it. They realized just a few years later that it was the same as what Schrödinger proposed, the Schrödinger bridge, 8 years before. Just at the moment, it was not clear. So he introduced it as a tool to compute. So at least, you know, we can give credit to Schrödinger for some part of optimal transport. So there is something good for quantum, but it's not for what you want. So I'm sorry about that.
There was a question over there.
Okay, thanks for your inspiring presentation. I really like the intuitive introduction about the optimal transport. You give a lot of good examples. And my question is about next slide. And you mentioned the
next one after this
slides about the convexification of the some problems. Could you please give some comments or?
Right. So what do I mean here? Okay, at the beginning, I would say there is everything. So at least for me, I remember when I first looked at this problem, this came from discussion I had with Quentin Merigot, who is in Paris, and he was running a lot of simulations for this kind of minimization problems. And he said, oh, every time I run a simulation and I run a gradient flow, okay, so you see what I'm talking about, a gradient flow. So you try to move this energy in the direction of the minimal gradient. What I see in my simulation is that things converge very quickly to the minimum. I don't see any issue. I don't see critical points that block my simulations. And then he was like, why it works so well? So what's going so well in some of these minimization problems? Of course, this is not only in optimal transport, but at least he was seeing this in a lot of optimal transport minimization problems. So it looks like in this kind of optimizations, problem of these loss type functions is that the gradient flow it behaves as if it was convex. So is there some convexification happening because of the high dimensional structure of it? So we asked ourselves, is there any theoretical explanation for this? And what we could do is the following. So I will try to give you slightly more technical answer to this. What you do is the following. Say, okay, what is the problem of a non-convex gradient flow, of a non-convex energy function? That you can get stuck at some critical point. Now, I don't believe that we will ever get stuck at a critical point unless this critical point is stable. So all of its, if I look at the energy functional and I compute its Hessian at that point, all its eigenvalues should be non-negative. Because if there is an unstable direction, the gradient flow will fall out of it. Of course, it's an infinite dimensional situation, but never mind. So I can take my energy functional, and I can say, let me compute all the critical points. I can write down the criticality condition. And let me compute what it means to be stable, which is usually some quadratic form being non-negative definite. And now we asked ourselves, can we characterize all stable critical points of this energy function? Usually this is impossible. I mean, these are like, because it's the space of configuration, it's huge. You have like a matrix which is, depending on the number. I mean, if your measure is atomic and you just work with the atoms, you have, I don't know, a billion atoms, then you will have a matrix which is 1 billion by 1 billion. There is no way you will get something there. But then we say that, okay, of course we never characterize all critical points, also because we know that there are some pathological counterexamples. You can build them ad hoc. But perhaps we can rule them out in some way. And then we said, okay, what happens if I only look at critical points as the number of points, or stable critical points as the number of Dirac deltas of the atomic measure goes to infinity. So I don't look at a situation where I have only finitely many points, but I take a lot of points. So in the limit as n goes to infinity, I have this huge space, which is the space of all possible limits of all stable critical points for the finite dimensional problem, right? So a priori this could be huge. And then it turns out that in many situations, that's what we managed to prove. In reality, as n goes to infinity, all stable critical points collapse to a single element, and this single element is the global minimizer. So the reason why the things go so well is because in the finite, so before n going to infinity, what does it mean this? It means that all stable critical points energetically are all very close to the minimum. So perhaps you have critical points which are very far energetically from the minimal energy, but they are all unstable. And so that's the way what I mean that it complexifies. So in reality, it behaves like a convex problem because in reality, all your enemies are all unstable. And then if they're unstable, no gradient flow will ever capture that, especially in a numerical simulation. You just miss all of them. And then you will only get stuck in some stable critical points, but from an energetic viewpoint, they're almost optimal because we proved that as n goes to infinity, all converge to the global minimum. So in reality, no simulation will realize that because then you're almost, even if you're almost optimal, you're as good, almost optimal is as good as optimal, right? So that's what I meant in my cryptic word, it convexifies.
Yes, thank you so much.
Thank you.
Any further? Yeah.
Hi, thank you for the talk. Well, just as a simple question, so for using this kind of models, like when applying to biological system or the things like cloud, do we need to assume population size is constant? For example, you have a figure with like a 20 points and move to another cloud, but how about if the particle will birth or some particle will go extinct, like die out, so then the population size change? How to deal with this kind of things?
So in the cloud, you don't have extinction population. So let's say you have 20 points. If I have 20 points, I will have 1/10. I just put same mass at every point. So 1/20 in each point, and they just move like this. Okay, so there is no mass loss. The problem is in the example of Schiebinger, the single cell genomics. Every time you measure, the mass reduces a bit. So then you need to put some term in your optimal transport which allows for mass loss. So this is something that there are many models now that can do that. So people introduce variants of optimal transport that allow for mass to not be preserved. Of course, it's an optimal transport problem plus some extra cost that you pay for killing the mass. So you can do it, but at the point, so there is no unique way of doing it. There are many ways of doing it, but you put this in the model itself. So you say, I don't know, imagine that I have two distributions, and one has mass 1 and the other has mass 1.1. I can first try to look how much it costs for me to send this distribution mass from here to here so that it matches a fraction of the mass that is here, because here I have more. And then I just pay a cost for the fact that there is a mismatch in mass. You see, first I transport, I'm missing something because I have less mass here than here, so I will not be able to take all points. And then I just pay an extra cost for the loss of mass, and how much I pay depends on what you're trying to model.
So even if they are birth events, for example, over time, some new cells produce.
Yeah, that's what Schiebinger, there is a paper, for example, Schiebinger with Yang-Yeong Kim and co-authors, I remember, where they develop a full theory of how to do optimal transport for this kind of situation where the mass changes in time. So I suggest you, so I don't remember the details of that paper, but if you look for Schiebinger and Kim, so Schiebinger and Kim, they're both at UBC, University of British Columbia in Vancouver. And if you look, they have some papers together, and I remember there is one of them where they really do the mathematical theory behind this kind of single cell genomics. It's a kind of a long paper.
Any further question from the audience?
Oh, there's one there.
Thank you for the very nice talk. I want to ask further about this slide and this convexification property. So you say the convexification phenomenon is only for some problems. And you said like for machine learning, like you cannot have this for all machine learning problems. So I want to know for which problems can you prove this and for which problems it doesn't work in the machine learning setting? What breaks down?
I don't know. I don't have something that breaks down. So let's put it in this way. I see convexity. So we took a model example of a very non-convex problem, which you just minimize. So we put the quadratic cost, and we just minimize W2 distance within distribution. This is a very easy problem to formulate, and it's very non-convex. W2 is not a convex energy. And for that problem, we can prove the statement I told you, that all stable critical points converge to the minimum. So it's not that I have a counterexample. So I think what we did is rather flexible. So I think I don't have a list of energy on which I can test, right? Because there are any model you give me, there will be you change some parameters. So I'm not sure that for every choice of models, it will work. But my impression is that in reality, what convexify this problem in many machine learning situations is that as n goes to infinity, this n goes to infinity is what creates the order. Now, so this is, I think, an intuition that probably many people have, but now in concrete situations, at least for us, when we just wrote down the formula and we tried to prove that, it was not that easy to do. I mean, like you just can play with the formula of being a critical point and being a stable critical point, and it's not that easy to work with that. So I don't have a counterexample. What I'm saying, I think when I say that maybe it doesn't work, it was just to be cautious. I was trying to protect myself not to make an overstatement, right? So in reality, I mean, even all the examples that, my impression, many examples that people have where they see, oh, the gradient flow here gets stuck or this training gets stuck, is only because the number of neurons is not very high. As the number of neurons grow, you get a higher dimensional problem, and high dimension just helps going around all these unstable critical points. I think so from a geometric viewpoint, it's also natural, right? So in high dimension, it's very difficult to create stable critical points. It's extremely difficult. So if you give me a random function in a dimension, most critical points will be unstable in reality. So I think that's the meta principle behind all this. Why it all works? Just because you are very, very high dimensional problem, and this allows you to move around all these bad points. But okay, this looks kind of perhaps not very much. So for a mathematician, we'll say, okay, but that's not a theorem, right? So yeah, and that's why we tried at least to prove something rigorous there. But so this, we see it in optimal transport. I think we see it overall in all this machine learning, and there is a lot of high-dimensional geometry also principle behind it. But okay, here since it was OT, I was making some also OT publicity. I hope.
Thank you. Yeah.
Thank you.
So with that, may I propose that let's close the session and let's thank our speaker, Professor Figalli, once more.